So welcome everyone to this course, Introduction to Quantum Materials. This is an NPTEL course which we will offer from today onwards all the way up to the 19th of January, as we had advertised. This is a sort of special or different course from what one would conventionally have encountered in a regular master's or even a graduate program, because it's designed to bring the forefront to you, although of course says that it is an introduction. So it's a different kind of introduction. It will be, the lectures here will be delivered by Professor Venkatraman Swaminathan, whom I have the pleasure of introducing as well as hosting. Although this is not a conference, since we are launching this course from here in Chennai as part of the NPTEL platform, it's really only apt that I mention at least a few highlights from the illustrious career of Professor Venkatraman Swaminathan. He is a very distinguished scientist and researcher in the area of materials science and quantum materials and nano engineering. Currently, he is an adjunct professor at Rice University in the Department of Materials Science and Nano Engineering. He's had an illustrious professional career spanning already of over 4 decades, which includes research and development both in government-funded laboratories such as the very eminent Bell Labs, as well as development in the industrial setting. And just to mention a couple of highlights, he's a life fellow of the IEEE, the International Engineering Society. He's a fellow of the American Electrochemical Society. He's currently a distinguished research fellow also at Lehigh University. We have also shared with you his profile based on a link. So all the lectures will be delivered by Professor Swaminathan. So I will be sort of playing an assistive role in the rollout of the course. I'm Shivaramakrishnan in the Physics Department of IIT Madras. And we bring this course to you from Chennai to wherever else you're attending from, apart from this studio here. Now I hand over the stage to Professor Swaminathan. But just before that, a few little course guidelines perhaps for participating in interaction. One of those is that in the announcement we made, we also informed you that in principle you can take this course for credit. That is, you get 1 NPTEL credit. IITs and centrally funded technical institutions accept this as a course credit, so you should have no problem crediting it. So if you're doing it, please keep your institution informed. Master students may find this more relevant, but research scholars also, to fulfill coursework requirements, may want to take advantage of this. But this is also a way to get us your wholesome participation in the lectures, in the assignments. There are just a couple, and the exam at the end of the course, which completes the evaluation, which gives you the credit. For those who are just as serious but don't want to take the tension of exams and the such, and want to really get immersed only in the scientific content, you can also just audit the course, but please attend all the lectures, which will always be from 4 to 6 p.m. On the working days from now till the 19th. We will share more details with you, including the course schedule, in case that is not already done. So for those who just attend the course without crediting it, if you have 100% attendance, you get a little certificate from NPTEL, which also can be valuable. Perhaps you want to take an advanced course on quantum materials data, for which this could serve as a prerequisite. We will also have a little attendance thing going on, both for students in person here and offline and online who are on Zoom. So Nikita and Sudarshan will help us with that. One of the important things is we are recording these lectures so that this can be shared on our national MOOC platform, NPTEL. So while we really want the course to be as interactive as possible, we will have a 2-hour session in which we deliberately introduce a break after 60 minutes to have a deliberate question answer session. If you have any pressing questions or clarifications in between, please raise your physical hand or the Zoom hand and draw the professor's attention. You will be given your opportunity to ask your question whenever we like. So it's just going to be like a classroom. So apart from your continued attention and as much peace and quiet as a lecture needs, we ask you not for anything more. So please bring in your curiosity and enthusiasm, and let's enjoy this course on which is on an introduction to quantum materials. Professor Swaminathan, it's yours now.
Thank you, Professor Shiva. Thank you very much for the nice and kind introduction. Welcome you all. Good evening, and good evening to all the people, entire Bharat, I think, listening to this lectures. So let me say as a few things about myself as an introduction, so that way you will get used to my delivery and you are able to hear me properly. And if you want me to raise my voice or something, then you can tell me so. I'm an alumni of IIT. I graduated in metallurgy in 1970, 65 to 70 batch. So when I entered in 65, that was the first graduation of IIT Chennai. Professor Sengupta was the director at the time. And we didn't have to do any monkey proofing because there were no monkeys on the campus. We didn't have any problem with that. So then I did my PhD and so on. So I'm in the third phase of my professional career. I spent 24 years in private or industrial R&D setting, then 14 years in government R&D setting in the US government. Then I retired from my job, and now I associate myself. This is the third phase, where I'm with Rice University and Lehigh University, and I was at Penn State as well. So spending my time in teaching, which I enjoy doing, and also particularly mentoring students. So that's a way of my contributing back to the society, to the scientific community, what all I have gained from in my 40 plus years of career. So this course is going to be an introduction, but I have selected a few topics because, as you can imagine, the area of quantum materials is quite encompassing. And I will define as I go along what are quantum materials. So I have selected, this lecture today will be a general introduction. So sometimes you might feel that you are drinking from a fire hose because there will be a lot of information, but that is intentionally done so that you get a bird's eye view of what are all the things that are there in the quantum materials. Then the rest of the lectures will be select topics. And I have chosen some topics to give a view of the forefront of research in those areas. Then we will modulate as I go along. And if you find it too difficult, we can throttle it down. Or if you find it too elementary, we can increase the level of the engagement. As Professor Shiva said, as I keep talking, if there are any specific thing you see you need clarification on the slide, please ask the question. Otherwise, hold your questions to the Q&A session that we will have at the end of each hour, right? And I don't mind staying a bit late if you are interested in also, talking to me. And also at any time during the rest of this week and part of next week, if you want to talk to me before the class, I can make myself available. Okay. So with this, let's proceed. You might have seen this already in your the information about the course. So we will have today two sessions, kind of overlapping, of course, a little bit. but a general introduction of the subject and the topics to be covered. And what do we mean by quantum materials? So I will talk about that lexicon, the taxonomy. Every material is quantum in some sense. Why now? Why do we call this quantum material? So we'll talk about the taxonomy a little bit. Then day 2 will be the select topics. So we'll talk about optical transitions, single photon emission, which is very important today for quantum materials, the new field of twistronics, then Janus materials, and some very exotic materials and quasi-particles. And the last lecture, and you notice here, the next week, January 18th, there is no class. The last class will be on January 19th, that is the Thursday. And there I will talk about some of the quantum engineering concepts. These are all emerging concepts, so we'll spend up some time in discussing them. If you kind of look at the evolution of materials through ages, so we have, going from the BC onwards, the Stone Age, Steel Age in the 1800 AD, then the Silicon Age starting in 1947 with the discovery of the transistor, then the Glass Age, plastic, compound semiconductors, which revolutionized the information age, then the discovery of graphene, two-dimensional solids, the van der Waals solids. Then now we have quantum materials. So this all led to the Industrial Revolution, as you all know. The Silicon Age started the digital revolution, a revolution which affected humanity. Then the information revolution with the advent of compound semiconductors and semiconductor lasers, which enabled sending data through optical fibers. So now we have a quantum revolution. So the 21st century is going to be dominated by quantum information sciences. So it's no more a dream, but it's going to happen. And that was marked by the Nobel Prize in 2022, which was awarded to these 3 gentlemen who did the experiments demonstrating that you can entangle photons. That was the first experimental verification of the Bell inequalities. And so that started the pioneering quantum information science. So this is a recognition by the Nobel Committee that the quantum information is a reality. If you kind of look at how things have happened in the last couple of decades, you have several disruptive technologies. On one hand, data-driven disruption. On the other hand, you have engineering-driven disruption. On the engineering side, 3D printing is very common now. Devices and sensors of many kinds. On the data-driven, we have Internet of Things. Platforms including smart cities, autonomous vehicles, etc. So the emerging forces on the horizon, right? So with the Internet of Things, we can have ambient experience. Technology is part of the environment. The interactions from reactive to proactive. For example, now my home is empty. I'm away from 6,000 miles, but everything is, I can monitor what's happening in my immediate neighborhood of the house. The ambient experience, I can experience that ambience even not at the ambience, but away from the ambience. Artificial intelligence is driving a lot of phenomena. As a result, we are going to have what I would term it as an exponential intelligence, artificial to exponential, meaning not only these virtual assistants, Siri and Alexa, Google, whatever, will be able to recognize and adapt to our moods, to our emotions as well. So in the same trend, emerging forces on the horizon, quantum is a reality, is going to be touching everyone's life very soon, perhaps even before end of this decade. You can scan large volumes of data for correlations and for exponential computation. So meteorological forecasts can be more accurate. Qubits for quantum computing. So you can have a qubit and increasing the computing power in an exponential way. Communication can also be very secure because quantum cryptography is almost unbreakable. Quantum sensing with the hydrogen vacancy center in Diamond, a lot of things have been opened up. You can have a possibility of an MRI imaging with hyperpolarization using quantum sensing so that one doesn't have to spend 40 minutes inside a very claustrophobic area to get your MRI image. All that can be speeded up in fractions of minutes. So that can revolutionize the health industry. And as I was saying, we can begin to see the impact by the end of the decade. So quantum materials are going to be the enablers of the quantum age. So the question really to ask is, what are quantum materials? Basically, all materials are quantum. If you look at the water molecule, 2 hydrogen atoms bonded to an oxygen, 3/4 of the body is made up of water. You can explain that constituency by quantum mechanics, but not necessary. A classical description is sufficient. So when would you want to do quantum if the periodicity of the lattice does not have to be taken into account? In the electron motion, classical description will suffice. But when that is not the case, then you have to go into quantum. Most phenomena in the macroscopic world, you don't need to deal with quantum mechanics. However, quantum mechanics is necessary to fully understand the behavior of materials. And that has come to fruition in the last 30, 40 years with the advent of silicon, the Intel microprocessor, which you can't explain the behavior of the transistor without invoking quantum mechanics, the motion of electrons and holes in the semiconductor. So the band structure of semiconductors, which led to the discovery of transistors, which led to the discovery of semiconductor lasers, you can see a very small footprint semiconductor laser can send terabits, picobits, petabits of information over the optical fiber. In addition, we now have the reduced dimensionality brings out very exotic quantum properties. We deal with 3 dimensions, but if you go into 2, 1, or 0 dimension, the confinement of the electrons brings out more exotic properties than otherwise realizable with the 3D. For example, graphene. Even graphene was discovered with the Scotch tape technique in 2004. But since then, the last 18, 19 years since the discovery of graphene, we are still discovering physics which hitherto was not even expected in graphene or in any carbon-based compound. So we are discovering new physics. Some of the physics in books have to be rewritten. So that graphene is showing that because of the two-dimensionality. Carbon nanotubes, one dimensionality, right? Again, properties which are not expected. Of course, now we have zero-dimension graphene quantum dots. Of course, this is an example that graphene paved the way for experimenting in reduced dimensionality. But there are many, many materials which are two-dimensional in nature and being discovered and also showing extraordinary physics, which nobody expected. So now let us redefine quantum materials. As I said, every material is quantum, but we don't deal with quantum mechanics if we are dealing with macroscopic phenomena. But when we talk about the electron motion in a solid where the periodicity of the lattice is comparable to the de Broglie wavelength of that electron, then we need to deal with quantum mechanics. But the result is very promising because you discover a new phenomenon and then new technologies, etc. So now let us redefine quantum materials. And this is the definition. This is the definition which is now accepted by the scientific community. Two notions are quite important, are prominent in quantum materials. One is emergence. Emergence literally means emergence of new phenomenon. And the new phenomenon comes because of strong correlation effects. The cooperative behaviors that cannot be predicted from the properties of individual electrons. For example, the high temperature superconductors, the cuprous oxide based superconductors. In addition to emergence, we add another layer which involving topology. This was also a new introduction into the physics of materials, where the geometric properties of the electronic wave function seem to also give rise to new phenomena. For example, the topological insulators. You can have very robust metallic surface states, the surface being metallic while the bulk being insulating. And also some exotic quantum statistics like the fractional quantum Hall effect is also a consequence of topology. So what do we mean now today? What do we mean by quantum materials? So these materials which reflect some properties as a consequence of electron correlation effects, number one, or it can be both or one, involving the geometrical aspects of the electron wave function. So if both these things are there present, then we would classify the material that exhibits this phenomenon as a quantum material. What is emergence? Yeah, excuse me. Did you have a question? Emergence is something very classic in all fields, not only in physics, in any field for that matter. Behavior not predictable from the knowledge of the constituents alone. And of course, you can even apply this to human behavior. How an individual behaves will be something, but the same individual behaves in a crowd could be different. It cannot be predictable. It may not be predictable. So emergence is not necessarily confined only to physics, but here in physics, it's a little bit more important because of the reason that it brings out some new phenomenon which is not otherwise thought of. Like a classic example of emergence is where the correlation is so important. I'm sure you all know how the flock of birds fly and how they navigate. Here, the navigation is not determined by any one bird in that flock, but it is an ensemble of all the birds contribute to the navigation. So this cooperative behavior, correlating behavior, is what we say emergence. And lo and behold, the fundamental particles such as electrons in solids seem to exhibit this. Strong correlation affects cooperative behaviors that cannot be predicted from the properties of individual electrons. I just put a simple example to illustrate this. What that cooperation really means is the whole is greater or different. It need not be greater, it can be different also. The whole is greater or different from the sum of the parts. You mix sodium and chlorine, you get the salt, which is not exhibited by any of the individual components of that salt. Superconductor, particularly the high temperature superconductor, the Cooper pairs are formed from the interaction between electrons. So that's a cooperative behavior. Of course, that cooperative behavior is mediated by the vibrations, the phonons of the crystal lattice. But different from the individual electrons, the Cooper pairs can share the same quantum state. And the consorted state, the shared state, can propagate without any electrical resistance through the crystal, giving rise to the superconductivity. So you have these two electrons joined together, behaving in a way not necessarily that can be predicted from the behavior of the individual electrons. For example, the high temperature superconductors, where high temperature meaning superconductivity above liquid nitrogen temperature. All these layered materials consisting of cuprous oxide. And the cuprous oxide, layers of cuprous oxide connected through some dopants like lanthanum, etc. And these superconducting properties are determined by the electrons moving within weakly coupled these cuprous oxide layers. So emergence, that is one ingredient of the quantum material. The other is topology. Now we have a large class of materials that have been discovered, materials which conduct electricity, does not depend upon local symmetries, but on non-local properties called topological invariants. And if the property is not defined locally, then it can also not be destabilized by local defects or fluctuations and so on. What that means is this topological property is very robust against any external perturbations. So the topological age now promises a class of materials with very robust properties which were not expected before. So now let us recap and look at what all I just said from a different perspective. The old way of looking at crystalline phases or phases of matter is based on symmetry, the Landau's famous classification of phases, purely based upon symmetry. The gas and liquids don't have as much symmetry as a solid. And even within the solid, the crystal structure plays a very important role in understanding the properties of the solid. But that is the old way. The new way is topology. Deals with properties that are preserved under continuous deformation and is useful to classify topological classes of matter. For example, between this donut and this cup, coffee cup or coffee mug, you have a hole and there's a hole, and you can continuously transform from here to there or there to here, from the mug to the donut or donut to mug, without tearing apart any of the material. In other words, a continuous deformation can achieve going from one topology to another topology, and I'll talk about the genus factor of one. And of course, that discovery won the Nobel Prize in 2016. So the Gauss-Bonnet theorem, which defines a topological invariance, properties of geometric objects that are conserved under continuous deformation, and which characterized by a genus G. The genus is nothing but the holes on the matter. So, for example, a spherical ball or a plate doesn't have any hole. A coffee mug or a donut have a genus of one with one hole. The glass is G2, a pretzel G3. So here we define a topological invariant looking at the curvature of that object. So we define a Berry curvature over the surface of an object, and we find that the Berry curvature is also known as the Pancharatnam curvature. Actually, Professor Pancharatnam came up with this idea and proposed it long time ago before Sir Berry refined it. So the Berry curvature over an object, over the surface of an object is quantized. And the number of this integral, the Berry curvature integrated over the surface, is the Euler number. And in the quantum parallel, we have the Chern index, which is a topological index or a topological invariant attached to the manifold of states defined over the surface. So for example, a genus of G0, you can distort the surface, continuously deform it, but the integral value doesn't change. Similarly, a donut, you can change it in any way, still is topologically invariant. So now, emergence and topology, we now reclassify the phases of matter. So electronic phases of matter are typically insulator, conductor, and semiconductor. But an insulator versus a topological insulator, the difference is you see a typical insulator, you have inside a conducting copper wire. The outside is insulating plastic sheet. But in a topological insulator, it is reversed. The bulk is insulator and the surface is conducting. And the surface, metallic surface states, conducting surface states, is purely a consequence of the topology. So we will see as we go along some examples of that. So topological insulator Ti is a new electronic phase. New electronic phase other than these three conventional electronic phases of matter. Materials that have insulating interiors, but metallic surfaces. For example, the 2D electron gas exists at the surface of an insulator, and it is topologically protected from disorder and other effects that would destroy its conductivity. So you can have a very enhanced electron mobility of the 2D electron gas because that mobility is preserved from scattering through impurities, etc. You all know what an insulator is. You have, suppose if you take an insulating material and you look at each, these red dots are say electrons, and then if you apply a magnetic field, then you have cyclotron orbits around each electron undergoes a cyclotronic orbit. And the band structure schematically shown here, energy versus momentum, is just a schematic picture, just to show that there is a gap between conduction band and the valence band. So the insulating state, which is the most basic electronic state of matter, exhibit a conductivity that is zero near absolute temperature. Because the insulating state occurs because there is a gap separating the filled valence band and the empty conduction band. Now, what is a topological insulator as opposed to the insulator which is the bulk insulator, the trivial insulator. The quantum Hall state, which is the simplest topologically ordered state, occurs when electrons confine to a 2D interface between two semiconductors and experience a strong magnetic field. So schematically shown here. So you have a semiconductor aluminum gallium arsenide and another semiconductor called gallium arsenide. So you have a heterostructure and there is an interface, the red line here. Suppose if you can trap a two-dimensional electron gas at that interface by doping the aluminum gallium arsenide with a donor atom like silicon. Since aluminum gallium arsenide has a higher band gap than gallium arsenide, the electrons will spill over to gallium arsenide away from the silicon impurities that it was originally bound to in the aluminum gallium arsenide. So what that means is the electrons which can be scattered by the silicon impurities are now separated. So you have a trapped two-dimensional electron gas, which can have an extraordinary mobility. And then now if you apply an electric field perpendicular to that material, that structure, then you have again the cyclotron orbits in the bulk. It completes the full orbit. But suppose the same electrons near the edge of this, on the two edges here, the orbit it will be skipped because it cannot complete the full cyclotron orbit. So it has to skip to the next one, skip to the next one, skip to the next one, etc. And as a result, what you see is you have conduction along that edge while the bulk is insulating. So now you have the same picture as before, a conduction band and a valence band separated by a gap, which is true for the bulk of the material. But near the edges, you have edge states, which continuously connect the valence to the conduction band. So electrons can easily travel across the edge. So you can have edge current. So there is no energy gap leading to perfect conduction in one direction. And these are called the chiral edge states because you see this chirality coming because of the skipped orbits. And of course, if chirality going in one direction on one edge, and here it will be on the other direction. And now you apply a magnetic field, then you can measure a Hall conductance. And that Hall conductivity, sigma xy, the transverse conductivity, is related to only the material properties or material constants, I should say, physical constants, electronic charge and the Planck's constant. And then this Chern number. The Chern number is the Euler equivalent, like the Euler number when the Berry curvature is integrated over the surface. So this Chern number is quantized. So you have quantized Hall plateaus when you do Hall measurements on a structure like this. And you can see phenomenally a great thing here that this transverse conductivity is only dependent upon the physical constants, has got nothing to do with the material. There is no material related property in that equation. It's purely fundamental constants. So it doesn't matter if this state, the quality of this material doesn't play a role in this conduction. So that is consequence of this topological chiral states, protected edge states, which is a consequence of this skipped cyclotron orbits that are forming at the edges, giving rise to continuous edge states connecting the valence band to the conduction band. The picture that I showed you is sort of a two-dimensional cartoon. Now you can extend this to three-dimensional as well. You can have a three-dimensional topological insulator. So here you have three-dimensional topological insulator. All the surfaces of this cube are conducting as pure electronic conduction, while the bulk of the 3D can be insulating. So for example, the surface states will be equivalent to forming 2D Dirac cones like you form in a graphene two-dimensional layer. So the 2D cones formed at the surface, giving rise to helical spin polarization, moving in one direction here, on the other end is the opposite direction. So the surface states of a 3D topological insulator are like that of an ordinary 2D conductor and are again topologically protected against backscattering. And is it only theory? No, it's experimentally discovered as well. Here there's a series of materials where these effects are discovered. In the 2D case, the quantum spin Hall effect insulator, exhibited by a very exotic heterostructure like cadmium telluride, on either side sandwiching mercury telluride. The beauty in this case is when you go from cadmium telluride, you have a normal band structure. You have the E versus K relationship here. But when you go to the mercury telluride, there's a band inversion. For example, the p-like states of this valence band, the s orbitals, like the conduction band of the cadmium telluride, are completely switched in the case of mercury telluride. So the band gap goes through a transition point from finite gap to zero gap to negative gap. And this sort of behavior is a hallmark of topological insulating behavior. So near this band crossing, where you get almost close to band gap of zero, like a semi-metallic type of behavior, there you get these topologically protected conducting surface states, and these are experimentally verified as well. So you have spin current, quantum spin Hall current, the red and the green on either edges like the chiral states, but these are now spin currents. And depending upon the spin, the direction of the current is changed. Spin of one kind, say going from left to right on the top, and the same spin will go from right to left. Spin of the other direction, the green, will go from left to right and right to left. So it will be opposite in either edges, but you have these robust spin currents, edge spin currents in the topological material on exotic structures like this. And these are dissipation-less because there's nothing to scatter them. So being dissipation-less, there is no power consumption. So dissipation-less spin current with a low energy consumption is what you need for spintronic type of devices. So these topological insulators are not just theory, are just only academic curiosity, but they also have tremendous practical applications. So we discussed so far what are quantum materials. So two important things, emergence and topology. Emergence means correlation effects, electron-electron correlation effects. In typical band structure calculations, you only take into account the electrons moving with the block functions of the lattice, and then is only take into account the electron attractive interaction with the ions of the lattice. You don't take into account the electron-electron interactions because they're very difficult to handle. The Hamiltonian becomes horrendous. But if you bring the electron-electron repulsive interactions and also the exchange interactions because of the spin exchange interactions, then the whole behavior is different. So that is emergence. The topology is the wave function of the electron is also sensitive to the immediate geometry of its environment. And that also you can intuitively visualize. I'm sure you all know about the Born-Oppenheimer approximation, right? In solving the Schrodinger equation. We typically only deal with the electrons moving. The ions don't respond, right? The ions are heavier. So typically all the time we will ignore that the ions are stationary, only the electrons are moving around, right? And the ions are just producing a drag on the motion of the electron. But that's okay. But if there is a rearrangement of the ions in the immediate vicinity of the electrons, that picture is not taken into account in the Born-Oppenheimer approximation. But if you bring that effect into this picture, then you treat the electronic wave function as though it is responding to the immediate geometry. By geometry, I mean the immediate vicinity of the ionic arrangement. Right? So that is how the topology comes into the picture. That's how the Berry curvature, Berry phase, all these effects come into the picture. So that is the second aspect, emergence and topology. Okay, all that is great, but now there is a third element or a third dimension to this interaction between correlation and topology, is the behavior of particles in a solid. So there we have to talk about quasi-particles. So this is a cartoon by Professor Matek at Caltech. So we have a real horse, a real particle, but here there is a horse. A quasi-particle is like a quasi-horse here. Here is a single particle, but here now it's an ensemble particle. That is, quasi-particle is therefore, you see it only in a solid, right? As a free particle, there is no quasi-particle. But in a solid, the particle is no longer free. It is seeing other particles of its own kind, and also the lattice. So the original individual particle plus a cloud of disturbed neighbors giving rise to quasi-particles. And the quasi-particle behavior is a hallmark in quantum materials. Okay. So emerging quasi-particles, particles which were not thought of before, are theoretically predicted, I should say, but not experimentally proven, are the Weyl and Majorana fermions, which are very important for quantum computing, and the very exotic magnetic skyrmions. These are all emerging quasi-particles. You won't see a skyrmion, pre-skyrmion, like an electron, but you will see in a lattice, in a solid. Again, a consequence brought out by the two factors, electron-electron correlation, interactive effect, and then the topology. So let us dive into these quasi-particles a little bit, the emerging quasi-particles, at least get a background of what it is. You all know about the Dirac equation. I'm not going to go through this in detail, but just to show you where the physics is coming from. This is the standard Dirac equation for a spin 1/2 particle, where c is the velocity of light, m is the rest mass of the particle, and the momentum operator, etc. And then you solve this for spin up or spin down particles with mass, a positive mass, or spin up or spin down antiparticles with a negative mass. And the Dirac electrons are the ones in graphene, behaves almost like light because they move velocity only reduced by a factor of 300 of the velocity of light. The electrons move very, unhindered in graphene. Now, this is the original Dirac solution. Right? So a spin up or spin down with positive mass as though and a negative mass, which solve that equation. But then, lo and behold, Professor Weyl, Hermann Weyl, a German mathematician and theoretical physicist, in 1929, he proposed another solution to the Dirac equation. He conjectured that the fermion would be a massless quasi-particle, but still carry electronic charge. So that is known as the Weyl fermion. So the regular fermion is an electron with a mass and a charge. But the Dirac equation can also be achieved with zero mass, but an electronic charge, a particle, like a photon with no mass, but there is a charge. This was only a theoretical prediction, but then almost 50 years later, Professor Hassan at Princeton University found that the Weyl fermions do exist in a very exotic material called, it's a semi-metal, tantalum arsenide. So with the discovery of materials, some of the physics which was thought of theoretically is now a reality. So now you have an equivalent Weyl fermion. And this, what is the so big deal about this massless Weyl fermions? We can immediately conjecture that with the no mass, it will move very fast compared to normal electrons. So that means you can create very fast electronic circuits. Furthermore, Weyl particles are topologically protected from scattering, which means they could be useful for quantum computers. So this is one emerging quasi-particle. Then the next one, Majorana fermions, Italian theoretical physicist. The 1959, there's a question mark, just this is an anecdote just on the site. Nobody knew what happened to him. He disappeared. And you can do the Wikipedia on him and it'll be very interesting. And he marvelously solved the Dirac equation and describing a neutral particle that is its own antiparticle. So imagine as though you split the electron into two halves. One carries a negative charge, the other carries a positive charge, its own antiparticle. So that is called, is half an ordinary Dirac fermion, as shown here, right? So this is a quasi-particle. Again, there was no evidence of Majorana fermions for many years, but recently in condensed matter systems, ion-based superconductors, there is evidence of Majorana fermions. And these two fermions are very important for quantum computing. The next third exotic quasi-particle, magnetic skyrmions. Magnetic skyrmions, like you see when a plane takes off, you see all these vertices of the vertex of air pockets. So it is a vertex like non-collinear spin textures. Like you have a vertex of spins. And they are topological defects in the magnetization texture of some materials. So in the peripheral region of the vertex, the local magnetic moments are directed upward, that is parallel to the applied magnetic field, whereas in the core, they are downward. So the blue versus the center versus the periphery. So you form this spinning vertices of spin structure, like a tornado, a quasi-particle. And do they occur? Yes, in fact. Originally, it was predicted by Professor Skyrmy in 1960, when he was looking at some soliton-like equations. And later, it was experimentally observed, predicted in 1960, this experimental observation in 2009. So it takes time because you have to have the material. So material discovery is a very important constituent of this whole thing. I will mention that towards the end as well. So the manganese silicide, iron cobalt silicide, monolayer of iron, they all show these exotic skyrmion structures. They all have a chiral lattice, non-centrosymmetric, ferromagnetic with the lattice chirality, like a staircase. And then you form these pockets of localized spin textures, the vertices, the vertex of spins. So that is the magnetic skyrmion. And the skyrmions show extraordinary metastability. So this is shown here, imagine this a free energy curve as a function of position. So you have two minimas, but there's also an intermediate minima. And the skyrmions are trapped here. So unless there is a very big activation energy, they're not going to go outside of that. So you can have very stable skyrmionic structures. What is so big deal about it is you can individually control them, move them from point to point without their vertex behavior, the texture not being lost. So what that means is you can store locally, you can act as memories. You can locally store memory, and that memory will not be lost even if you switch off the power, topologically protected, and you can move the memory from place to place. So you can do all logic operations as well. So this is the technological application, but coming from a very exotic physics, quasi-particle. And this is the last one, which is really raising the eyebrows type of quasi-particle, a particle called eneion. Eneion. Eneion means it occurs only in two-dimensional systems. Eneion means it can follow any statistics. It can follow a Bose statistics, or it can follow Fermi statistics. So things that can follow any statistics is called eneion. Only in two-dimensional systems. And they are used for topological quantum computers, and you can braid them. You can make a qubit of the eneions, and the operations will be protected by topology. So you can see the greatness of the material discovery leading to greater physics phenomena, and that not just doesn't remain in the academia thing, but it can also be used in the technology. So that is how this whole quantum materials field is moving very fast, and it's advancing. Every day new physics comes out. Okay, so it's 4:53. I will stop here for a few minutes before doing the next round, so we can take up questions from here or online, whatever. So
how can we for memory?
say it louder, I can't.
The
Skyrmions, yeah.
That energy landscape you showed, how it can be used for the metastability. So
Because in the metastability, if the skyrmions are here, it's very hard to disturb them unless you supply a lot of energy to take it away from that metastable state. So whatever information that is stored, if you can logically store information in that pocket, it will stay forever. So it is topologically protected because of this extraordinary metastability.
similar to the spin glass.
Yes, yes, yeah. And also in metals, there's a very well-known phase transition called spinodal decomposition. That's also exactly like this kind of a free energy behavior, where you have a metastable state, which is, you say metastable, but seems to be more stable than the ground states. Any of these areas, if you want to do more, study more, I have given references a lot of places, so you can take a look at them. And I cautioned you that it's going to be like drinking from the fire hose, because there's so much information I have given, but in a very high level bird's eye view. But all these are happening simultaneously. That's why the breadth of the field is so much that you can get lost in that. But there is excitement. Excitement on two grounds. One, you are discovering new physics every day. I will tell you, that physics textbooks have to be rewritten. You can't use old textbooks anymore, because these are all phenomena that were not known before. But then the excitement is also technologically is very important. Anyone else on online? Yeah.
So it's a question from Ranjit. what is the temperature dependency of topological phenomena? Experimentally, does these compounds always show topological property at room temperature or also at high or low temperature?
Many of it depends upon the material. Some materials are phenomenally show behavior only at low temperatures. So therefore, then we have to bring it to application. We have to do something. But there are materials which show topological behavior at room temperature, like the bismuth-based compounds are topological insulators at room temperature. So you have both. It varies. That was the only one? Yeah. There's another one. Yeah.
From Abhinav, can you once briefly topological aspect of materials with some examples?
So online students, you can also speak up. We should be able to hear you, principal. If you unmute yourself, you can speak up and in the interaction session, speak to Professor Swami. So if you have maybe someone can try saying hello.
Hello.
Okay, so we can hear you. So please go ahead and ask your own question, especially in the question answer session. Otherwise, you can, during the lecture, please raise your hand to interrupt and ask a question. Yeah.
Okay. Thanks, sir. So, my question is topology is only geometric behavior, or is it only a geometrical aspects of material, or we find it in experimental way, or there is experimental verification of topology in materials?
Yes. The question is, are they experimentally verified? The answer is yes. For example, this behavior of the transconductance, trans-Hall conductance. So if you plot the Hall conductivity as a function of magnetic field in a material like this, in a standard system, you will see that it varies linearly up to certain magnetic field. But then if you keep increasing the magnetic field, it will show the plateau type of structure. And all these plateaus corresponding to the C squared over H, and then the constant C, and the C is an integer. So C is varying, that's why you get different plateaus. And wherever there are plateaus, the log sigma xx will be 0. So you will see like this. So this plateaus that you see in the sigma xy, these are all experimentally seen in this material structure. That is a consequence of, I think I pressed the wrong button, so I erased it. But anyway, that's a consequence of the topology, because this number C is a topological invariant number. So that is one. Then here, quantum spin Hall effect insulator on this exotic material, mercury telluride sandwiched between two cadmium telluride, you see a band inversion. So at this point, the band gap is 0, close to 0. So again, the resistance as a function of a gate voltage where you can inject electrons or holes in the structure. And you can see very high, this is resistance, note that. So very high resistance, a low conductance. But then as you keep modifying that layer structure, you will see the resistance is dropping, and you see the plateau corresponding to, again, E squared over H, and then the constant invariant, topological invariant. See this green and red, right? So this is an indication of the quantum spin Hall effect insulator. So it is experimentally seen in the structure. And a lot of these bismuth-based compounds are called tetradiamides. They are all room temperature topological insulators. Again, showing bulk insulating properties and surface metallic properties. So to answer your question, it's experimentally seen in many, many systems, many material systems. Did that answer you?
Yes, sir. Thanks.
Yes. Okay, so we will continue. The exotic materials of many, many varieties, many types, coming under the banner of quantum materials. So I will now introduce some of those in the rest of the class. The Kegome crystals. Kegome means a bamboo basket in Japanese language. Kegome is a bamboo basket shown here. The beauty is you have these triangular structures, corner sharing triangles. So there's a quasi-hexagonal symmetry and reminiscent of the hexagonal lattice of graphene. So you can see the triangles whose lattice points each have 4 neighboring points. Each one of these have 4 neighboring points, so corner sharing triangles. So this exactly looking like the Kegome, the basket. You have materials showing this triangular lattices. And this is a very exotic crystal. And you will be surprised that there are many naturally occurring crystals. Herbert's smythite. You know, these are all named by the crystallographers or people who found these crystals. So they go by their names. Herbert Smith is the person who discovered this. So this is called Herbert's smythite. So if you want your name to be famous, you have to go to Mahabalipuram and find some crystals, some rocks, it may be exotic. Then your name will go on history. But the beauty is this triangular formation of the structure, and this is the chemical compound. It's a zinc hydroxide with the chlorine atoms, zinc copper hydroxide with chlorine. All of them are of the similar type, and here you can see another zinc copper hydroxyl compound. This was capellasite, and Capella is the crystallographer who discovered this. Naturally occurring crystals. Then verborthite, that is a copper vanadium hydroxyl group. Then visignite, barium copper hydroxyl group. The common thing in all this is this exotic triangular structures, triangular lattice. Now, what is so great about this triangular lattice, and this is where the physics comes in. Suppose you have a Kegome lattice like this, right? And then you look at the spin part of the Hamiltonian, right? Just to illustrate, suppose in an antiferromagnet, right? The spins, naturally the crystal spins will tend to align themselves opposed to each other. Each neighboring atoms will have the opposing spins. So that's the natural ground state, the low energy state. Suppose you take a triangular lattice. So you put a spin down, the electron is spin down at that corner. Then in this corner is spin up. So right here you satisfy, it's antiferromagnetic. But what do you do with this? Suppose if you put a spin up, then it is okay with the reference to this point, but then it is same spin as this one, which is, it doesn't like to have the same spin in the neighboring point. Or if you put it spin down, it is okay with this, but not okay with that, right? So this third spin is what we say frustrated, right? Like we get frustrated, we don't know which one to talk to. Like this spin is frustrated. So the frustrated spins want to anti-align. That is a natural state, but now here we have a conundrum. So then the crystal, of course, the intelligence that is built in, right? So we have what is known as an Heisenberg antiferromagnet on a triangular lattice. They all turn themselves to make sure that we have the net spin as 0. Right? So a fertile field of studying frustrated magnetism in these Kagome crystals. And somebody was talking about, I think, spin ice or spin glass. And these Kagome crystals are the field where you can look for these. Okay, so that is an example of an exotic material. So like this, we have many, and this is one example. Now, shifting direction a little bit, okay, with the quantum materials, we have to also embrace quantum phenomena. Quantum materials is one thing, but if you want to for quantum information, we have to bring in quantum phenomena. What do I mean by that? So we have been saying so far that two notions are very prominent in the field of quantum materials: topology and emergence. Right? Emergence is correlation. Topology is the wave function of the electron, depending upon the geometry, the immediate geometry, local geometry. But in addition, to bring the scientific and technological potential of the quantum materials, we have to leverage quantum phenomena. What do I mean by quantum phenomena? Such as entanglement, superposition, coherence, and qubits. So it's a paper, a perspective we wrote beginning of last year. So you can look at that for more details on some of these, but I will quickly go through this. So entanglement, right? Entanglement means particles that originate in close proximity to each other or as part of even a single particle that have been split have a correlation with each, no matter how far they are apart. They can be even across the universe, still there is a correlation. That is called the entanglement, photon entanglement, etc. So that is why Einstein called this a spooky action at a distance. What is this quantum entanglement in a simple way that we can understand? So here, we flip coins. So you flip a coin, there is 50% of it can be head. Two people are spinning coins, and so it can be head or tails, right? But suppose you put it through a quantum entangler, just Gedanken experiment. It's a quantum entangler. What that means is the probability of coin 1 flip and coin 2 flip are no longer independent of each other. So you bring this to our physics world. So you have a spin. So suppose you have a spin up, spin down. So you have a wave function, which is this written like this superposition here of these two spins, right? The result of measuring, and then you separate them apart. So one spin you retain and the other spin is elsewhere. If they are entangled, that means they are correlated. The correlation remains even if the spins are separated over large distances. In other words, if this is spin up, the other one is spin down. Result of measuring either spin is random, but the measurement of both are correlated. So Einstein called this a behavior, a spooky action at a distance. What has this got to do with the quantum? Is in the quantum information, suppose you want to communicate using quantum bit, and then you want to secure it. That is, it can't be broken. It is purely secure communication. So you use entanglement behavior. So you take a photon, split into two by polarization or whatever, and then say those two photons are entangled in this manner. Keep one photon with you and send the other photon through the fiber and goes elsewhere. And if that photon is somebody interrupts it and measures it, I will know because I have a photon whose state is correlated with the state of the other photon. So when that photon is disturbed, this is disturbed. So therefore, this way I will know if anybody tampers on my communication. So that's why he called this, he couldn't believe it. He called this spooky action at a distance, but now it is verified experimentally. That's the Nobel Prize I told you in the beginning. I'm not sure how to work this animation, but anyway. Then the superposition. Quantum superposition and qubit. Okay. So the principle of quantum superposition states that if a physical system may be in one or of many configurations, arrangement of particles or fields, then the most general state is a combination of all the possibilities, where the amount in each configuration is specified by a complex number. So you have a classical system, they are all closely spaced, but in a quantum system, the allowed energies are quantized. So through a classical lens, the energies become denser and denser and become continuous. So quantization is not noticeable. So we don't know this in everyday objects. But in a quantum superposition, a qubit is a coherent superposition of the basis states. So suppose if you have a linear combination of 0 and 1, alpha 0, beta 1 with a with the probability amplitudes. And then when we measure the qubit in the standard basis, according to the Bound rule, the probability outcome of 0 with the value 0 of this function with the value 0 is alpha squared. Probability of outcome of 1 with the value 1 is beta squared. So they are constrained by this relationship. So now the qubit in the superposition does not have a value in between 0 and 1, but have a probability alpha squared of the value 0 and a probability beta squared of the value 1. So in other words, superposition means there is no way even in principle to tell which of the two possible states forming the superposition state actually pertains. So now the states in 1 are represented by 1 or 0 or 0 or 1. So the quantum entanglement, now you can take care of this by this function here. So in this state, an equal superposition, there are equal probabilities of measuring 0, 0 or 1, 1. In other words, there is no way to tell if the first qubit has a value of 0 or 1, and likewise for the second qubit. But once you measure, then you know what the value of the other qubit is. Okay. Then decoherence. So just stating this here in a simpler way. So that means that a pair of quantum particles can have 4 possible states, and 3 quantum particles can have 8 possible states. And so these numbers add up very quickly. So you get enormous computing power with the qubits. Now, decoherence. The quantum particle remains superposition until it is disturbed by noise, temperature, or whatever, and loses its quantumness. So that is called decoherence. In other words, all your quantum computation has to be made before it decoheres. So it retains the coherence, quantum state. And the qubit is unlike the digital 0 or 1, the classical bit. The qubit is a superposition of 0 and 1, not a 0 or 1, but a superposition of 0, 1, both the states combined together. To intuitively understand it, if you flip a coin, it is head or tail, you can tell definitively only when it falls on the ground. If the coin falls on the ground, you know whether it is head or tail. But when it is spinning, you cannot tell. Meaning, when it is spinning, it has a superposition of both head or tails. That's all the quantum bit is. We are not talking about a 0 or 1, but a superposition of 0 and 1. So you can't tell. So you can only say the probability of 0 as that alpha squared, the parameter, or beta squared of 1. But with the constraint, alpha squared plus beta squared is equal to 1. So this quantum phenomena, quantum materials, we talked about quantum phenomena. Quantum phenomena is entanglement, superposition, the qubit, and the coherence time or the decoherence of the qubit. So this is the quantum, these four constitute the quantum phenomena. And now you have to leverage the quantum materials to the quantum phenomena to get a quantum application. Say, for example, quantum communication. That's one of the applications. So what is it? So you have a quantum cryptography and communication. So suppose you have a trusted private network. On one end is a sending person and the receiver, another trusted private network, right? You have a public channel. This public channel, even if you encrypt it, anybody can break the encrypt with these modern computers. So it's not secure. But suppose you entangle that photon which is going on this fiber from this network to that network, and then you send that entangled photon as your cryptography on a secure quantum channel. So therefore, there's a quantum key distribution. So the receiver gets a quantum key. So the receiver who has the quantum key alone can get this information, not anyone else. This is based on that quantum phenomena called entanglement. Right? So you can use this quantum phenomena to get very secure communication. This has been used already in places like Swiss banks. When they send account details, Swiss bank, nobody knows who has what. And so they will always be communicating, use quantum key. So therefore the account informations are all secure. Nobody will know. Japan does a lot of the banking through quantum key distribution. But that is in a small scale. Now imagine that you want to communicate with your friends and nobody can eavesdrop on you. You use a quantum key. So that's the quantum cryptography, leveraging the quantum phenomena called entanglement. Quantum computer. You all have read about the Google's quantum computer with the 53 qubits. That means 2 to the power of 53 processing, about 10 power 16. A very significant progress, but not still enough. That is in 2019. And they made a big claim, but that claim was challenged in 2022 that they can do much faster than the Google quantum computer. And there are close to 200 companies organized using our taxonomy, primary focus is on software, while 20 companies are making quantum processors and chips. So you can see the growth of quantum information age. This is a purely an imaginary, all quantum processing, but it will happen at some time soon. What I call it as a quantum chip, not as an Intel chip, but a quantum chip. So the input, whatever the input could be, any information, it could be anything, and there's an output. So this chip takes the input, puts it out, and it has quantum sources, it has quantum memory, it has quantum processors, it has single photon detectors, SPD single photon detectors, and then it sends that information out. So all processing is quantum. So it is secure, faster, and if you use topology, topologically protected, robust. So this is the future. The quantum materials are on the ascent, right? Employ a vast portfolio of compounds and phenomena where ramifications of quantum mechanics are demonstrated real. Quantum materials afford the exceptional value, symmetry, topology, dimensionality, and strong correlations in macroscopic observables. So you have the basic science, communication, computation, simulation, sensing metrology, and of course you have to have education and training. People have to be trained like we are doing now, right? People have to know what quantum materials are, quantum phenomena are. New software, new algorithms have to be developed. We can't use the conventional quantum, classical algorithms. We need engineering and control for the reason that you will lose the coherence. If you don't have the control and the engineering is not done well, then decoheres. Once it decoheres, all bets are off. So the exploration of the ways and means of creating new states of matter in quantum materials and manipulating the phases, various external stimuli. And then you can make new photonic, electronic, and energy technologies that would benefit humanity. What do we have to do to make quantum materials? Making new quantum materials from old ones. You have to just configure them differently. So you have temperature as one parameter you can leverage. Pressure, magnetic field, you can make 3D or lower dimensions. So you have a very wild and very large parameters that you can control. Temperature, magnetic field, pressure, doping, strain, coherent light, etc., to make a variety of quantum materials. So material discovery is a very important aspect of quantum materials, quantum phenomena. So discovery of new materials, how do you do? You have to have a very solid theoretical foundation. So this material discovery has to be backed by theory. So the many universe of quantum materials, there are an Avogadro number of particles, and which means this Schrodinger equation is a time-dependent Schrodinger equation. There are 10 to the power of 23 coupled equations. So the quantum mechanics problem is a big data problem. There's no way you can deal with this. So you have to make approximations, and there the density functional theory plays a very big role. Some of you may be involved in that. And Walter Kohn won the Nobel Prize for that TFT. So it reduces this many-body problem to the construction of a functional of the electron density. So you have the many-body perspective. So you have the electrons interacting with the ion. There are many electrons with a single ion. This is many body perspective. The DFT perspective is it changes this electron cloud into an electron. I mean, it changes this electron ensemble to an electron density by replacing them with some functional potentials. So it can reveal about the interpretation of the prediction of the complex system behavior at atomic scale. But while it is helpful, the DFT has limitations for strongly correlated systems. Now you can see that this is difficult. Now, if you on top of that, you have the electron interactions. And then the electron, this is the repulsive interaction. And then the exchange interactions. So this has simply the potential of the ions interacting with the electron, which is an attractive interaction. And then you treat it with the block functions and so on. But when you add these additional two terms, then that Schrodinger equation becomes even more complex. So we need to do a lot of advances in theory. The DFT is the starting point. So we have to discover, there has to be a concerted effort in discovering materials. Then the experimenters can then with that knowledge can go and experiment in the lab, which materials to make. So I want to touch upon quantum sensing. That is another element of quantum application. So very briefly, what is the ingredients of quantum sensing? So you have a two-state quantum system. So a lower energy state and a higher energy state separated by an energy, h omega naught. So you can look at two phenomena to leverage for quantum sensing. One is whether anything can change this transition energy. So exploits the changes in the transition energy, or something which affects the transition rate. Suppose you kick an electron is here on the upper state and it is returning to the ground state. That transition rate, will it respond to an external signal? Or the external signal will affect the transition energy. So you can use that for sensing. So quantum sensing is typically used to describe one of the following: use of a quantum object to measure a physical quantity, which can be classical or quantum. Quantum system is described by quantized energy levels, which can be electronic, magnetic, or vibrational states. You can use quantum coherence, that is the spatial or temporal superposition of states, to measure the physical quantity. You can use quantum entanglement to improve the sensitivity or precision of the measurement beyond what is possible classically. So the type 1 and the type 2 are close applications than type 3 in terms of sensing. For sensing, what is the most important criteria is sensitivity. Sensitivity is defined as the minimum detectable signal per unit time. That is the minimum detectable signal that yields a signal to noise ratio of unity for an integration time of 1 second. So it is given by this formula here. And the important thing here is this coherence time. So dimensionless, C is a dimensionless parameter. The Euler number and gamma is the coupling or transduction parameter of the quantum signal. So you want to have a very large coherence time to have a small V minimum, which is the high sensitivity. So, you know, the minimum value of that V minimum, it shows high sensitivity. High sensitivity means you can measure very weak signals. You should really, a good sensor should have high sensitivity. Even though we use the word high, what that means is it measures the lowest possible signal. So the advances, the quantum sensors will be definitely going to be made possible because of better materials, precise control, long coherence times, efficient readout, and thus higher sensitivity. For example, in the coronavirus detection, we still don't have anything which will have absolute 100% positive result, right? There will always be false positives, false negatives. Suppose if you imagine a quantum sensor, then you can have 100% confidence that there's a false positive means, or I mean, a positive result means it's a positive result, not clouded by that it's a false positive. And that brings to this topic of hyperpolarization. So I mentioned the coronavirus deliberately because health industry can greatly benefit by quantum sensing. Hyperpolarization, what is it, hyperpolarization? Hyperpolarization of molecules using nitrogen vacancy centers in diamond. Nuclear magnetic resonance, MRI, everybody is aware of it, everybody knows. It's a bread and butter of health industry. But if you go through an MRI, which I have gone through, you sit in this chamber and you have to lie motionless. Sometimes, depending upon what they have to scan, it takes 40 minutes. You have to be in that claustrophobic environment. And you pray all gods at the time. You go crazy. It's such a narrow space and it makes loud noise because some magnetic field is there and they take repeated measurements to build the signal to noise ratio. And the room is very cool because the magnets have to be cool. So you are uncomfortable. If a person is claustrophobic, he or she, and you have to stay motionless for 40 minutes, 50 minutes, sometimes an hour. Suppose if you have to, I have had 2 major back surgeries, this back spinal column mapping means an hour of sitting there in the MRI. All this, why I'm saying is the reason why it takes such a long time. The nuclear magnetic resonance, which is the operating physics principle of MRI, it originates from nuclear spins. Nuclear spins have very weak thermal polarization. It's only of the order of 10 to the power of -5 for protons in a magnetic field 3 Tesla. So that is a major limiting factor for the sensitivity of NMR, and spatial resolution is poor. That's why you have to keep building statistics. You have to repeat data taking. Imagine now you can do this hyperpolarization. What is hyperpolarization means? You transfer the spin from one medium to the spin of the nuclear spins of the target object. So you create a higher spin polarization, a spin with a higher thermal polarization rate, and then enhance, instead of 10 to the power of -5, you enhance that exceeding the threshold. So you can do this almost increase by close to 90%. And the nitrogen vacancy center complex in diamond, whose electron spin can be rapidly in microsecond and efficiently polarized at room temperature, right? So if you can transfer this to the nuclear spin in whatever the target medium is, then, and this has been conceptually shown to be possible, then you can cut down that 40 minutes or 1 hour scan time to few minutes of scan time. So this hyperpolarization will just revolutionize the health industry. So this is a humanity affecting contribution of quantum sensing if it can happen, and it will happen. There are already companies in Europe trying with this idea. All right, so I gave you some really important technological consequences of what quantum materials can bring. So an outlook, direct application of quantum materials, you can have communication, sensing, computing. What are the interactions that you want to pay attention to in the material itself? It can be photonic. You can use photonic manipulation of the material, electronic, spintronic, or even take advantage of the lattice vibrations, phononic. Like for example, polaritons. Micro nanoscopic implications. So you can electronic band structure, the fundamental thing of the material. Optical properties, we are going to be looking at this in the next class. Thermoelectric for power generation, mechanical, chemical, batteries, etc. Structural, morphological, magnetic. So many properties that can give rise to implications in these applications. How does it benefit humanity? Energy, environment, because quantum computing can enable meteorological forecasts to be more accurate. So you can predict tornadoes, floods, tsunamis, etc., much more accurately. Global weather patterns. Biology and medicine, I told you about MRI. So I have given a few articles for further reading if anybody is interested in getting into these areas in somewhat deeper manner, and you can get a background of some of these. I think that may be the last slide. So I think we have almost close to 20 minutes of time, that we have enough time. So I'll be open to any discussion, questions pertaining to this, and in general about quantum materials that you may have.
I have a question.
Yeah.
Regarding quantum computers, like I've just heard about photons currently being used as a qubit. Is it true, or they're working on some using electrons or even some spins or materials?
The Google quantum computer was using the tunnel junction of Josephson superconducting junctions. The IBM quantum computers also use the Josephson junctions. So Josephson junctions is the superconducting current. The on-off state of the superconducting current is the qubit. So that is sort of electronic. There are no, as far as I know, demonstration of a photonic qubit yet.
But we have heard more about photonic entanglement.
No, the photonic entanglement is in terms of, for communication purposes, not necessarily for computing purposes.
Any online questions? Please speak up if you have questions online. This is now our question of the session. So Swami, maybe I have one question.
Yeah.
Well, what are the prospects for quantum memories with these materials?
Yeah, the quantum memories, especially with the magnetic skyrmions type of structures, which are topologically protected. So the quantum memory can be used there, and it will be very robust for storing the information, because it will never be lost. Even if you switch off the power, it is still there, that kind of thing. And then you can manipulate that memory. So quantum memories, quantum repeaters, you need quantum repeaters for quantum communication. So these are all emerging areas in quantum, yeah.
You say entanglement one photon is connected to other. So what's the medium?
The photons can be sent through free space or it can be sent through fiber. Just regular communication, except that the photons are entangled. So therefore, for this, you have to have a single photon emission. So we will talk about that in the next class. What are single photons? Why do we need single photons? Because you have to maintain, each photon should be indistinguishable. If suppose you have a photon pulse coming through, each one should be indistinguishable, and they should be, you can make superposition that way. And what requires, what is needed to make single photon emission? So we'll look at photon statistics and then how single photons have to be made. That will be tomorrow's session. Not tomorrow, day after tomorrow. Tomorrow I'll talk about the optical properties.
Yes, from online.
Yes, sir.
Introduce yourself if you can.
My name is Abhinav.
Yes, Abhinav.
Yes, sir. So, sir, my question is related to entanglement and superposition. I am always confused between these two terms, superposition and entanglement. Suppose I have two electrons. So these two electrons can show four states, up, 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 down, then up plus down and up minus down. One triplet and a singlet. So what's the really difference between entanglement and superposition?
No, they are related. It's not, they are not two different things. They are related. So you entangle the photon, whatever either a photon or an electron or whatever it's let's say a photon, but then you have to build the superposition to build the qubits in terms of quantum computing. But then in terms of quantum communication, there is, you send the entangled photons. There you don't superposition.
Okay, sir.
Professor.
We are not able to hear you. There is some we are not able to hear you. There is, your voice is breaking, so you can type your question in the chat box. If there is a bandwidth limitation at your end, we can read that out and pose the question to the professor. Meanwhile, we'll take a question from the class.
Yeah.
So you spoke about mention about anions, wherein they can take any
Statistics.
So are there any specific conditions in which they go from one, like they cater to one statistic versus other statistic? Are there any specific criteria in which they exhibit certain statistics versus the other?
No, what that means is, so if it is, suppose if you have two particles, let's say fermions, and then the two particles, and then you exchange them, and then you exchange them again, right? So you bring it here, this one comes here, then you go back to the original. But in that process, the wave function would remain the same, right? If it's one exchange, the fermion case, it becomes negative, then again it becomes positive. In case of boson, nothing happens, it's a thing. But in the case of the anion, it can change. The two exchange of two anions can change their wave function. So like fractional quantum Hall effect is one example, and there are other examples as well. So therefore, you can now have, in the picture that I showed you, and the picture that I had, that cartoon. So you can have, so one anion, the other one, when it is exchanging in its place, you can sort of braid around it. So you can make these braids. So that is the braiding anions. And then you can make two anions to form a qubit. So like this, very exotic structures, and these anions can Abelian or non-Abelian statistics. So this for quantum computing, these are all emerging ideas. And then again, I have given this Wikipedia article reference. You know, just take a look at that. But it occurs only in two-dimensional systems. Where you are okay with the flow and the delivery, you are able to follow. Is it clear? Is there anything else that you want me to modify? In tomorrow's lecture, you will probably find that there's a lot of information on slides. So you can give me a feedback whether you want to throttle that down or not. Sometimes too much information also it's not easy to follow. But you are otherwise able to follow me. Okay.
So the online previous question was from Nagendra Babu. So the question was the role of cupric oxide in superconductors.
The role of
Cupric oxide.
the cuprous oxide of
Cupric.
C2O. That is the the cuprous oxide is essentially that's where the superconducting Cooper pairs are formed, and they are separated by spacer layers, and the electrons are moved within the weakly coupled cuprous oxide layers. The Cooper pairs are, and the neighboring layers contain ions such as lanthanum, barium, strontium, other atoms, which inject electrons or holes onto the Cooper oxide layers, which then form subsequently the Cooper pairs, which are not mediated by the phonon vibrations as in the regular superconductors. So the correlation effect is in the cuprous oxide doped with the lanthanum or strontium or whatever. So it's a very complex interaction. So you have to look at the phase diagram of the cuprous oxide with the lanthanum or any other dopant that you put in. So basically it will be, this could be some component X, or it could be strontium. And the role of lanthanum and strontium are the ones supplying the carriers, which move within these layers of cuprous oxide.
Thank you, sir.
Yeah. You know, I in my lectures, I devote, each one of them is a lecture by itself. So this will be one class where I'll be discussing this more in detail. But you know, since it's all condensed, this gives you the overall bird's eye view. Anything else? Just as a way of creating some discussion. Okay. I made a point that for many situations, macroscopic behavior, you know, you don't need to invoke quantum mechanics. So the periodicity of the lattice does not have to be taken into account in the electron motion. Classical description will suffice. How would you prove or disprove this? What would be the criteria for you to say, no, I now have to invoke quantum mechanics. So suppose if an electron is moving in whatever medium, don't worry about the medium, and things that can affect that electron, just sake of argument, some obstacles, something that can drag the electron motion. So the electron is not free to move, right? So I'll do something like this. So some points are sitting there, and they can have an influence on the electron by dragging the electron. Suppose if the distances between them are very large, as opposed to a situation where it is like this, what would be the condition for you to decide that this may affect or may not affect, while this will affect?
If we take a wave function and the wavelength, they are kind of interacting.
So correct, exactly. So you have to look at the de Broglie wavelength of that electron, right? What is the electron wavelength? If that wavelength is of the order of that lattice spacing, then you can't treat that the electron will be independent of the medium, right? So therefore, this condition is necessary if you compare. So how will you calculate the de Broglie wavelength? You have to know the velocity of that electron, which is typically the Fermi velocity. So you can probably verify this for yourself. Look at the Fermi velocity of, say, copper or something. Calculate the de Broglie wavelength and look at what is the interatomic spacing in copper. They'll be comparable, of the order of 2 to 3 angstroms. So then in that case, you cannot ignore the wave function of that electron anymore, because it is now of the same order as the spacing between the ions. Right? So that is the criteria. But in many situations, that's not relevant. But here we can't do that. So just to have a discussion, right? That's what happens in the case of an Intel processor, right? The transistors. So in the case of the transistor, what would be the parameter or a characteristic that would tell you that you cannot deal that system without bringing quantum mechanics? A transistor works basically on a PN junction, right? It's a diode. So what would be the criteria, or not a criteria, an important parameter in a PN junction? Right, so you have a junction. This is the Fermi level. So this is the N type. This is P type. So this is a diode, depending upon how the voltage is applied, whether it is forward biased or negative biased. So the electron either will flow or it will not flow, right? That's what a diode is. But what determines that? No, I need to bring, I worry about the quantum wave function. What would be the parameter? Like the de Broglie wavelength, an electron here, there's a hole here, right? They have to go to their contacts to flow a current, right? You have to connect these leads. You have to apply a voltage, right? So that when you reverse the voltage, no current flow. But if you, So they have to come to the contacts, otherwise you don't collect any current. So before so many things could happen before they come to the contact. It's like traveling on the roads. So many things can happen. Suddenly the light can change. There could be a pothole, you can have a flat tire. So what could happen here? What would be the equivalent to that length scale?
Barrier height.
Yeah, the barrier height is important, but electrons doesn't go to this side, they have to go to the contact. The holes don't go here, but go to the contact. Right? This barrier, that's what it does. It's a barrier for electrons. Similarly, there's a barrier for holes. The electrons have to diffuse. So therefore, the characteristic length is the diffusion length. And these lengths are very small again. So therefore, to understand this, you have to then talk about how the electrons move, and you have to deal with the band structure of the semiconductor. That means quantum mechanics. Same thing in the laser. Any light emitting device. So basically, we have to filter down to the fundamental parameter that deals with the particles like electrons or holes. Then only quantum mechanics comes important. Right? Can I ask you one more thing to think about? This is a two-dimensional graphene. This won the Nobel Prize, discovered in 2004, and the Nobel Prize, I think, was awarded in 2010. Novoselov and Graham, they won the Nobel Prize. So it's a two-dimensional, a flat sheet graphene. So carbon atoms, flat. Imagine one single layer. And this is same thing, but it is rolled into a tube. This is the carbon nanotube. This is two-dimensional graphene. So my question is, why does the tube doesn't fold back into a flat sheet? Or vice versa, why doesn't this fold into a tube? If this is graphene, so let's say, and it's just, imagine there is a thickness here, but graphene is much thinner. Why doesn't it do this? And suppose if it is, why doesn't roll? Suppose if it is rolled, I roll here, it opened up. It doesn't remain rolled. Why doesn't the carbon nanotube roll back? What makes it to remain as a tube? What would be the physics parameter that is important? Both have bonds. They both have the same sp2 hybridization bonds, right? Not sp3 because now it's two-dimension here. So the third dimension, that orbital is empty, so pz orbital. So therefore sp2 hybridization. Here it is sp3. 3p orbitals and one. Carbon has 4 sp3 electrons. So you tell me the answer tomorrow when we meet. Okay, all right. Good evening and see you tomorrow. So tomorrow, just to quickly, yeah. So we'll talk about optical transitions in 2D transition metal chalcogenides, talk about excitons, Valley Electronics, and we'll talk about infrastructure. In case I'm not able to cover everything on this class, it may spill over into the class on Friday. And the Friday class will be single photon emission, nitrogen vacancy in diamond, and other 2D semiconductors. But here I will be discussing phonon statistics. Okay, if you have any other questions tomorrow, if you want, I can come early, we can talk. If that's okay. Yeah, instead of 4 o'clock, I can be here around 3:15 or something. 3:30 perhaps. 3:30 we can start. All right, good evening.
Thank you, Ben. So thanks to the online audience as well. So we'll keep the session open tomorrow from 3:30 for discussion. The lecture will start at 4. So we'll have some semi-formal or informal discussions before the lecture begins. So please present yourself if you'd like to discuss. Thank you, everybody.
Sir, could you please share your phone ID? I can check your Google Drive and you can want to upload today's slides into so that we can share it with the students.
Oh, okay, that'll be good. Nice.
You can write it down. Take a photo of it and I will share it.
Class 100 per 0 last 100.
Yes, we 25. Oh, okay.
So you will give me a Google access to Google Drive, you will set up a Google Drive.
Yes, sir.
So then I will put today's slides
Okay.
and also tomorrow's slides.
I think sir, PDF will be much lighter.
But because I use those animations, that's why. But if PDF is okay, then I can do, which is better.
PDF also is fine. If the animations are not overlap, then
No, in PDF, all that will be collapsed. It won't have any animations, but that's okay. You still read the animation. I use it for the purpose of talking.
yeah, that's right. For
Presentation. So I can do that. If it's for students, I can make it PDF.
fine. Sir.
That
PDF
is
is also fine. Much lighter.
Okay, then PDF is only a few megabytes.
Yeah. Okay, sir.
Because these are pictures, it comes out to be 25, 30 slides. And the email. Anyway, you then, should I send you the PDF to you?
Okay, sir. I'll send you a mail in this email ID. So you can reply to that and send the PDF. Sir. So
Okay.
I'll share it with all the students. We have a Google group. Sir.
Oh, okay.
Or we have WhatsApp group. So both I can share it so that they'll have the information about it. Sir.
Yeah, definitely. Yeah, they should have the slides. Yeah. Otherwise, they can't retain it.